Welcome to the thesis defense on printing on a cloud for modifying wood-based constructions. My name is Felipe Martinez, and I am an industrial design student at the University of Applied Sciences, Amsterdam. I took part in this thesis due to the desire to learn about the world of computational design and robotic production, due to their potential for creating innovative industrial design solutions and entailing design approaches that were new to me at the time. In this presentation, I will guide you through the work that I have done at the Robot Lab. The project I worked on was about developing a demonstration of printing on a cloud for modifying unwanted or used wood-based products. Some conditions apply to this project. One of these conditions is that the demonstration had to be producible using the tools available in the Robot Lab. Additionally, the printing on a cloud demonstration could not consist of a process which could be carried out without the printing on a cloud technology. Printing on a cloud is a technology developed by the Robot Lab, which facilitates creating and carrying out operations on non-standard and non-planar surfaces. Robot Lab wants to explore how to apply the technology to add value to wood-based products. Lumber prices have been soaring since the corona pandemic and have remained high while demand has soared. The majority of products live a short lifespan due to becoming undesirable, leading them to become waste while remaining functional. The greater goal of this project is to combat this global issue. The central research question in this project is, what printing on a cloud process and wood-based product combination best demonstrate the technology's power to extend the desirable use life of unwanted products? The central research question will be answered by analyzing 5 questions concerning printing on a cloud's processes: the target audience modification preferences, the best wood-based construction for using in the demonstration, valuable computational design tools, and exploring how printing on a cloud can be a circular process. To begin the analysis, the question is asked of what specific processes can printing on a cloud for milling wood-based products carry out. And in this question, we'll find out what processes the technology can carry out, as well as the specific processes that make the technology innovative. Printing on a cloud is a technology developed by the Robot Lab, where curves get projected onto a 3D scanned object to become toolpaths for a robot arm. Printing on a cloud's workflow begins with scanning the input product to create a digital representation of the object. The next step is establishing the digital and physical models' calibration reference points. After calibration, the to-be projected curves are input. Here one creates the toolpaths by inserting 2 or 3-dimensional curves onto the printing on a cloud program and orienting them to the desired placement. With the toolpaths created, a selection can be made of which tool will be used to process the input product. Virtually any tool that can be attached to the robot arm can be used in the printing on a cloud process. The final step of printing on a cloud is production. In this step, the input product is modified with the created process. The technology has the ability to carry out toolpaths which follow a surface accurately and homogeneously. Using the robot arms opens up the possibility of using various tool attachments to the machine. Additive processes such as milling, drawing, and FDM 3D printing can be carried out with printing on a cloud, and milling and laser engraving are subtractive processes the technology can carry out. It was decided that there would be a focus placed on milling for the project. The reason for this decision is that milling requires little pre-processing, creates a permanent effect which is both perceivable visually and physically, and is a process with many different changeable parameters, such as milling depth and milling bit type. Furthermore, the milling paths allow placing additives such as 3D printed paths or paint onto milled areas as a post-process. Comparable technologies exist that can carry out processes similar to printing on a cloud milling, or milling on a cloud. One such process is laser engraving, which in some setups is done on a robot which allows the laser's line to stay on the normal surface area, creating homogeneous engraved lines. Another similar process is using a traditional 3-axis CNC milling robot to carry out the process. For such a process, however, precise models must be made of the to-be processed product to create the milling process without having the scanning technology that printing on a cloud uses. Having analyzed the comparable technologies, it became clear that milling on a cloud's advantages over these technologies consists of the speed at which a milling on a cloud process can be prepared, scanning and all. Additionally, using a 6 or 7 axis robot arm provides a great amount of range and access from the robot, and the integration with computational design allows for many benefits which involve mainly form freedom and complex pattern generation with ease. The next question stated is, what is the ideal target audience and what modification processes can milling on a cloud produce which are most valuable to them? First, research was conducted to find the ideal target audience for the project. Millennial professionals were found to be the most promising target audience to focus on due to their high awareness of the importance of sustainability, while also having limited funds to allow them to act on this awareness. This group is also one which has mostly not settled down and is busy upgrading their furniture and products every few years. User research was carried out on the target audience through a survey and interviews. This user research aimed to discover the perception of value that the target audience has towards their products throughout their useful life. With this research, it was discovered that the target audience most values aesthetics, comfort, personalizability, and durability. A causation diagram was created with the insights of the user research. Afterwards, a diagram was created using the found insights to display potential milling on a cloud modifications that can be carried out on wood-based products, which the target audience values most. Based on the research on the target audience, a decision was made to focus a project on creating modifications which stylize the modified products. The third sub-research question is, what type of input product is the most valuable to combine with printing on a cloud milling? The goal of answering this question is to identify the wood-based construction that best works as an input product to demonstrate the innovative ability of printing on a cloud. Research was done on different wood-based constructions, mainly in IKEA, because it is the largest user of wood in the world and it uses an extensive range of wood-based constructions to create a wide range of affordable products. 4 different wood-based constructions were identified, which are used by IKEA for their products. These constructions were identified as chipboard plus veneer, solid wood, stacked bamboo, and plywood. The 4 found constructions were compared using a matrix, where they were assessed on how they fulfilled the criteria already established. Plywood came out as being the only construction which fulfilled all of the criteria. This is due to plywood being able to be molded into forms with curved surfaces, and it being a construction that, when milled, doesn't expose much weaker materials, which is the case with chipboard plus veneer. 2 products were chosen for testing milling on a cloud. These products were an IKEA stool and a skateboard deck made out of molded plywood. A V milling bit was used in all the tests due to its ability to create milling paths with different widths based on the milling depth. The first milling on a cloud test to be carried out was on the skateboard deck. The surface which was processed was covered in grip tape right before the processing occurred. When the grip tape was removed, a large plywood surface with little to no surface wear was exposed. The process's results, though not perfect, showed smooth milling lines, creating an enormous contrast due to the plies on the skateboard construction being colored differently. In this test, we also observed different ways in which the pattern can interact with the processed surface's edges, as you can see here. The next test that was carried out was done on the IKEA stool. This product had a wood which was measurably softer than the wood used for the skateboard. This test aimed to test out the limits of the milling on a cloud process and what it takes for the process to fail. The milling lines were visibly rougher than on the skateboard, even at shallower depths. And because we used deeper milling depths as well as denser patterns, this caused the material to chip away at some areas. The lessons learnt having carried out the tests are that there are precision limitations in the technology. Also, restraints have to be placed on the pattern density and milling depth based on the material of the construction to ensure desirable results, among other things. The final physical model made for this project is a production prototype, which aims to display what milling on a cloud looks like when successfully applied to a molded plywood product. For this test, it was decided to use a shallow milling depth as the lines create a large contrast at this thickness already, and it was desirable not to have the milling lines intersect as this caused problems in the previous test. The 4th research question asks how computational design can be used to add value to the final demonstration when incorporated into the making of the milling on a cloud process. This research began by exploring computational design broadly to find what computational design tools are relevant for the project. The generation of complex curves was found to be an essential computational design tool type, as these tools can create a wide variety of different complex patterns. 2 general types of pattern generators were discovered: growth simulating and field-based pattern generators. The kangaroo talus pattern generator is an example of a growth-based pattern generator, and it grows onto a surface, populating it to different extents based on the settings of the program. The Metaballs pattern generator is an example of a field-based pattern generator and creates curves surrounding input points on a 2-dimensional plane. The curves can be projected onto a curved surface. However, warping occurs with these 2-dimensional projections onto 3-dimensional surfaces, unlike the growth-based curves which account for the curved product's form. Another computational design tool type which was discovered to be valuable for use in the design process are trimming tools for the surfaces. These tools are helpful for limiting the area where the pattern is populated when that is desired. Next to pattern generation and limitation, computational design is a very valuable tool for generating unique forms with almost no human effort and for creating and controlling complex geometries. The final question addressed in the analysis is how milling on a cloud can be applied to a circular business model. Circular design is an approach where one designs products to not fit into the linear economy, where once a product has been used in its first use life, it gets thrown away. When designing for the circular economy, a product will get put back into the cycle of use through recycling, maintenance, or other things displayed in the butterfly diagram. Printing on a cloud has been found to be able to carry out processes that fit into the category of maintenance and prolonging. Because of this, printing on a cloud is most at home in the business model called the gap exploiter model. In this model, exploitation concerns the leftover value of the used or unwanted product. Circular design goals have been created to strive for a demonstration which is as circular as possible. The first one is to have the modified product inspire attachment and trust in a user by allowing the user to affect the product form or aesthetic through interaction. Another goal is to create a product that does not disturb a user by looking ugly, plain, or annoying by creaking during an interaction, for example. Research resulted in a list of wishes and requirements, which will be used to assess the ideas and concepts generated in the following synthesis phase. In the synthesis phase, divergent research is done in the form of different ideation sessions, and concepts will be generated from them. Both sketch and computational design ideation were carried out in this project. The sketch research began very broadly by exploring what could be done with milling on a cloud, even exploring processes that could add function to the construction as well as aesthetic. After this, sketch ideation was carried out, focusing on aesthetic engravings applied to the plywood products. The following ideations would be carried out in a computational design workspace, using the pattern generating and limiting tools to create process ideas. The result of this divergent research resulted in a selection matrix entailing most of the design options possible with the made design programs in Grasshopper. This matrix would be used to generate the final three concepts. Concept 1 is an engraving process applied to the IKEA Benjamin stool. The engraving simulates a section of Hawaii's topographical map and is made using the Metaballs program. This concept takes advantage of the V-bit's ability to output a variety of milling widths by having some lines be thickened than others to simulate a topographical map even further. The pattern has only been applied to the product's top half to demonstrate how limited patterns create a contrasting aesthetic on the modified product. Concept 2 uses the kangaroo talus and mirroring to create a projected pattern which simulates but matched wood. The pattern is populated on the entire top part of the concept and has a power of showing how computational design can output unique forms with a predefined logic. Concept 3 uses two different pattern generations to decorate two skateboard decks' top surfaces. The decks in this concept have switched functions from being a skateboard components to being hangable pieces of decoration or art. The purpose of this concept is to display an upcycled canvas showing art made with the help of robotic production and computational design. Deep milling lines can be applied into this concept as it requires much less structural strength in its new function of hangable decor. A Harris profile has been created using the wishes generated in the analysis phase. The highest scoring concept out of the three concepts is concept 3 because it does not need any post-processing, is strong for its new function, and reacts well to being milled with smooth milling lines. The concept was further developed into a skateboard canvas art gallery concept, which displays three different ways of using skateboards as canvases with milling on a cloud for displaying computational design art engraved by a robot. This variation of skateboard canvas is a highly detailed milling on a cloud process onto a single skateboard deck. The goal of this variation is to show the process in its highest quality, and the lines become visible only when observing the model up close. From afar, the process can be perceived as a blur. This second variation of the skateboard involves using multiple skateboard decks to create one large canvas, displaying one image. This variation can be expanded to a user or artist's desire by adding more boards, allowing for the creation of more prominent decoration modifications. The third variation, nicknamed the Island Duo, uses two canvases to display two different types of pattern generation, which contrast nicely with each other. The reason for making this variation was to demonstrate the diversity of computational design. The value of this concept is that it displays printing on a cloud's unique value of being able to process surfaces homogeneously and precisely on non-standard curved objects. When it comes to the skateboard canvas art gallery, printing on a cloud is a process which has the potential to turn waste into a canvas for high-quality engraving processes, formerly only producible by an artisan's hands and requiring a lot of time. Using printing on a cloud, such processes can be produced efficiently using the robotic process to even automate them and, of course, make them a lot quicker to carry out. The concept ties in well with the target audience, who have various budgets, a general interest in the skate lifestyle, and want to show their uniqueness through the products that they own. And computational design could also give them a say on the aesthetic of their eventual product, which will be theirs. When it comes to printing on a cloud's ability to add value to wood-based products, it should not be constrained to one type of product. The process has proven itself very powerful when mixing computational design with a non-standard product stream, which means it can process virtually anything with the right tools. The next step for this project could be to develop printing on a cloud further to be automized in creating the to-be-processed digital surface and also be usable with other types of constructions next to the plywood. A scenario that I can see for the future of printing on a cloud is one where it is not only used to make products or art like the skateboard canvas art gallery, but having the technology also be used for creating a sort of Einheitskunstwerk in an interior. This would be achieved by modifying multiple objects in the interior with computationally generated forms. The role of an industrial designer in the world of printing on a cloud can be one of a researcher who gathers information about the problem that printing on a cloud can answer, then research to identify what desirable outcomes are most beneficial to the target audience, and expand or optimize programs to achieve those desired outcomes. I am Felipe Martinez, and thank you very much for watching my presentation. Goodbye.